This video is proposed to introduce you to the different mission profiles that are often used during preliminary design stage. Simulation models must give the possibility to compute quantities that permit to choose the components. These quantities are often linked to phenomena that degrade the component, such as torque, speed, temperature, pressure. We have to compute these quantities using scenarios representing the system in operation. These scenarios can often be represented by mission profiles. That means effort and speed as a function of time at load level. We're going to represent here these mission profiles. Simulation models are more developed in the multi-physical modelization module. Here we can see the spoiler example seen in the previous video. One of the points we made was that 5 operating scenarios were enough to cover all the different design drivers of the actuator. These scenarios can be represented by lump parameter models and inverse simulation. Software used can be MATLAB, Modelica, Excel. Lumped parameter models and direct simulation. Softwares used can be MATLAB Simulink, Modelica, AmSim. And distributed parameter models and finite element simulation. Anyway, it's fair to say that most of the cases can be represented by system-oriented simulation. Here, we're going to see the differences between direct and inverse simulation by using an example. Let's suppose that we want to compute the necessary force to move a mass for a transient displacement and a given effort. For direct simulation, a control loop helps us determine this effort, but it requires to properly set the correctors. For inverse simulation, we can travel back up the power chain from the load to the power source. These acausal simulation environments make that possible in simple cases. It is possible to only use spreadsheets. On this slide, we'll have a few examples of typical mission profiles. First, an operational situation where power variables remain constant. This profile can be represented by an operational point in a power plot, speed, torque. This operational point can be used to size a device which has a constant functioning, such as a cooling fan, or a device where inertia is negligible, an hydraulic jack for instance. Secondly, a sinusoidal profile. They can be used to size under lifetime objectives or size an energy source. Third, a pre-calculated transient profile, or point-to-point displacement curve. And finally, we have here a transient response to a common reference. Several applications can have a profile that describes the displacement that remains at the same value once and for all. For example, a landing gear lowering or an elevator displacement. Here are a few examples that concern pre-programmed displacement profiles. We visualize displacement, speed, acceleration, and jerk, the acceleration derivative. We also call them S-shaped curve regarding the displacement curve shape. The speed profiles can be parabolic, trapezoidal, or sinusoidal. These different profiles give for the same displacement d during a certain time t the shape of different characteristics. The maximum speed can be linked to the voltage supply of the motor. Maximum acceleration can be linked to inertia and motor's maximum torque. Jerk can generate vibrations in a device which has a resonance mode. These shapes can be linked to power losses in a motor. Regarding the application and its constraints, we'll be able to choose a profile favoring one of these criteria. Transient mission profiles are used to simulate critical operating cases such as transient temperature rise or short circuit while moving. To simulate the dynamic response of the system to a step, physically impossible to realize with a limited power, these steps references can come from discontinuities created by a simulator or be the result of a command from a higher level in the system. When it is necessary to represent in a simple way a closed-loop system's response, we can use a second-order filter which gives the possibility to represent the dynamic response of small signals. For high amplitude signals, power limits of the system can be detected on the response. To respect this last issue, it is possible to add saturations in acceleration and speed to the second-order transfer function. For an electromechanical actuator, acceleration limits are linked to the ratio between max effort and equivalent motor inertia. Speed limits are often linked to voltage supply of the motor.